Is the answer C? Could the answer be C? am I right?
Alright guys, let me catch up to you real quick. What'd you guys get for number 1?
C.
Yeah, why is it half? Yeah, 0 to 5. What about number 2? B. Why is it hemispheres, not a whole sphere or a quarter sphere?
Hemisphere is half a sphere.
Yeah, the theta goes all the way around, right? Theta goes all the way around, but I cut everything to be above the XY plane, so I cut my spheres in half, poor little dudes, and it is between two spheres, like between two ferns, because it's 1 to 3 for the spherical radius.
Don't listen to me.
How are we doing so far? Is that all right? I mean, those weren't too evil. Number 3. This one's a nice one. X squared plus y squared cylindrical is basically polar. So x squared plus y squared is r squared. What do when you raise something with a power to another power? You multiply the powers. It's scary how quickly those kind of rules go out of our heads. So it's just going to be r cubed equals 1. I like it. What about number 4 though? In spherical, what acts like r? Okay, I know what you mean. Yeah, rho sine phi acts like r, so this is going to be rho sine phi squared. The over 2 cancels, you end up with this. So see how these really are the same equation if you realize that rho sine phi is r. Right. Ooh, that's nice. Stop it, please. Okay, number 5. Let's see, the volume of a right circular cylinder with a base of radius 4 and by plane at height 5. Which one of these is that? So how did you figure this out? What'd you do?
Well, this one, R is 4, so 0 to 4 works. So C is out.
Yeah, which one? Yeah, which one can you take out of here? I mean, it's kind of silly.
This is the only one that has R in the R.
This is the only one that has R in it. That's kind of a bit of a giveaway. And does it do everything else? R goes from 0 to 4. It's got to go all the way around so you get the whole cylinder. And Z goes from 0 to a height of 5. So that one does everything it's supposed to do. So that was a little too easy. It's the only one that could be it because it's the only one that's got the right DV. Alright, that was silly. Oh, too bad. This one we already talked about. It's going to be C. Realizing this is phi there. Whenever it says without integrating, it pretty much means treat it geometrically. So what shape does this make? I've gone and written over these things.
Makes a sphere.
Is it perfect sphere?
Yeah, it'll be 0 to 2 pi, 0 to pi, 0 to, what's that say, 2?
3.
3, okay. So it's going to be all the way 0 to pi, all the way 0 to 2 pi, and then 0 to 3, it's just the sphere of radius 3. And what's that? What's the volume formula for a sphere?
4/3 pi r cubed.
Good. So then you just have to do 4/3 pi times 3 cubed. So it'll be 36 pi. Right? 36 pi.
I thought it was a stone. Not B.
Yes, yummy, yummy. Speed eating contest stuff there in search of. Same thing here. What's this going to be?
Cylinder.
We're in cylindrical coordinates. That's kind of a giveaway. So yeah, it's going to be 0 to 3 tells you what?
The radius of 3 per cylinder.
Radius of 3. And then it's got a height of 2. And then theta goes from 0 to pi, so that's a
half cylinder.
Yeah, so this is a poor little cylinder dude that's been cut chop. So you just want half the cylinder. So you do the cylinder formula, pi r squared h, cut it in half. So what do you get? The radius was 3, so it's 9. The height was 2, 18 divided by 2 is 9. Looks like it's part A. Sure. Let me stop there. How's that? Good, good, good. Let's see, number 9. Now this is where things definitely get more interesting. You do have to kind of think about what this means. So this is what y is doing. Y, so what's happening in the xy plane here?
Circle.
Circle. I like it. So my xy, let's see. I'm going to say this. xz, 0 to 2, negative 1 to 1, and this is going to be this circle. Yeah, so how do I want to put this together? So if I want to go to, they want us to go to cylindrical coordinates. This, of course, just becomes r squared plus z squared, so unfortunately they all look good. I can kill this guy, though, because there's no r. I like it. Now, which one of these is doing what I want it to do? So the main difference is the 1 and the 2. Yeah, the radius is supposed to be 1, and the height is 2. So it should be this guy. But you could draw it all the way out. Since this is why I don't like giving multiple choice, because you can do what we just did, which is process of elimination, and not completely understand what's going on. But you could do like I started to do and start to do traces and try to reformulate it into cylindrical coordinates. But this one was pretty easy because it gave us a bunch of stuff to play it off of. 10, same kind of thing, except now I want to go to spherical coordinates. So this piece is going to be
Rho
cubed, and it can only be C, because what are the other ones missing?
The other row squared.
The other row squared. So then you can double check to make sure they didn't make another typo. But
I don't get. Shouldn't phi be from 0 to 2 pi since it's just a complete the whole sphere?
Oh no. So again, phi only ever has to go from 0 to pi because theta goes from 0 to 2 pi. So for every possible value of phi, you sweep, sweep. Yeah. So you don't. Otherwise, you start to recount the other side. Yeah. I like it. Okay. So the last thing for today. Oh my God, Jeff. Oh shit. Before I go on, I'm going to make section 15.9. I am going to talk about it. I'm going to bring a little something next time, but because this is the section, I hate to make this extra critical, but I have to do something to keep us on track. This is the section that's got this cool-ass Jacobian thing. Some of you guys have heard of the Jacobian. If you took diff Q or linear, you've used the Jacobian. And it's a tool that, if you use it, you can prove that dA in polar is r dr d theta. It just comes out to be a matrix of all the partial derivatives you can do. So the same thing works in 3 dimensions, and then it can prove just as easily that rho squared sine phi is that extra piece, right? So the extra piece, the r is the extra piece when you go to polar or cylindrical. The rho squared sine phi is the extra piece, and that's the one that's determined by the Jacobian. And it really gets interesting about, you start with a rectangle, and then you enter a transformation. You can make the rectangle look like whatever you want it to look like, to be honest. And this would keep track of what must happen to track those changes in lengths as you did those transformations. That little extra piece is what makes the integration come out correct because of that change. So it's an interesting section to read, but we desperately have to get, chapter 16's got some more important stuff in it. Unfortunately, I hate to say that because this stuff is really, really cool.
So that basically this just lets you turn any surface into any weird surface.
Cylindrical and spherical are 2 of an infinite number of possible transformations you can make. So they are 2 classical ones that are used a lot, but there are people that use their own, entirely their own. So then they can use the Jacobian to figure out what that little extra piece should be for their specific transformation.
Do you know what it is for hyperbolic planes?
Off the top of my head, no. Did I once know in my life? Yes, I did. I remember knowing but now no. So I just want to do the barest little bit of this.
It begins function that maps R2 instead of two-dimensional vectors.
I'll make it extra credit then. 15.9. Extra credit.
Extra credit.
It's a really good section to do. Some of you guys are thinking, no, it's a good section for me. Not All right, guys. I just want to do a couple off of this real quick. We'll finish this up next time, but this is section 16.1. Oh, yes. Does this look familiar? So yes, there are truly such things as force fields. I mean, you know electric fields, magnetic fields. Some of you guys know more than you wanted to know about them. So this is purely the math behind a lot of these things. And in fact, to be honest, if I drew some level curves out, like here's a level curve, the gradient at any point, can somebody tell me, let me just tell you, let's say this is 1 and this is 2. Yeah, it must be perpendicular, and it's defined at each point. So at every point, the gradient is going to point, and it might be bigger or smaller at certain points, depending on how close it is to the next level, how quickly it's rising. Do you guys get what I'm saying? So here it's rising pretty quickly, and here it's really pretty far away, and so forth. But it's going to have to be everywhere orthogonal to that level curve. So I could graph at specific points, not every single point, because that would take an infinite amount of time. I could sketch all the possible vectors at each point, and that would be a vector field. So we've already dealt with vector fields. We just dealt with them at a specific point at one time, but you can imagine drawing all of the vectors at every possible point, or representative vectors. So just look at the back real quick. You get stuff like this. What does this look like that you've seen possibly? It's a really cool website that I might pull up next time that's got this. But if you ever watch the news, do you know that they still show the news?
Weather.
Yeah, weather. There's actually a website that shows you the wind velocity and direction at any point on the Earth at the current moment. So you can see, like, when there's a hurricane, it gets really interesting, or when there's a really big storm, it gets really interesting. Anyway, so that's one type of vector field that you can look at is wind speed and direction, right? So, for example, here's what a vector field function would look like. This is a vector valued function. So the outputs are vectors. So for any specific point, it's going to have a vector output. So for example, so if I wanted to draw, so I gave us little tiny dots here. So if I wanted to do 0, 0, obviously would be what vector?
0.
0, 0. Or that's amazing. But let's say like at 1, 1. So for x, y, 1, 1, what's the value of f going to be? 1 half, 1 half. So at 1, 1, I can draw 1 half, 1 half. So it's going to be like that little vector there. What about at 2, 2, 2, 2, as I have my 4 cube? 2, 2, 1, 1. So from 2, 2, I could draw 1, 1, so it would look like that. So obviously as I move out, it's going to get larger because it's dependent on x and y. What about along the axis? So what about at 1, 0?
1 half is going on.
1 half, 0, right? It points where?
Up the axis, right?
No. 1 half, 0, so it points this way. Now, do you notice how later we start to mix and match? The y's go in the I hat, the x goes in the j hat, and that's where things get interesting. That's where you get like rotational fields and stuff like that. You can have them. So this is me just divided by 2 so that I could fit more of them in the picture, right? And this is me normalizing them, making them all unit vectors. You see them? Huh. All right. I like that reaction. Okay. So I at least wanted to show you that 16.1. Now, of course, what we're going to do is stuff like, okay, if I took a path through this vector field, what would then happen? Well, it depends on, am I walking through wind? And I'm talking about the total exertion, the total work I'm going to do? Am I talking about something moving through an electric or magnetic field? Am I talking about what? So we're talking about the math behind integrating through a vector field. Ooh, that sounds just so neat. And we're going to get to what's called contour integrals. So we've already done integration over just a specific region in my input plane. We've already done that. So now I'm saying, instead of a region, let me just integrate over a specific curve. So I only take the outputs that are above that curve. So that would be the next kind of idea beyond this is contour integration. Line integrals, contour integrals. So that's all in our future. That's plenty enough for today, guys. I've loaded you down with enough stuff.
On that question, I wasn't on chapter 15.6. I wasn't sure if I was doing this system. So at 0, 0, 1, the Z is equal to.
Oh, that's right. The example we were doing was off.
I guess you too.
I'm doing college after this week and this weekend.
Yeah, I mean, UCs have to be done
By November 30th.
Yeah, so that's what 2 weeks away at the most.
Yeah, but their essays are standardized. You only have to go
No, man, it's 4. There's one required and 3. You have to pick 3 from the list.
Oh, that's right.
And then you can just figure out how
That is a lot more than I expected, but
Yeah, but I think it's max like 350 words each, so it's not.
oh really? Oh, so they're short essays.
Relatively short. I feel like short ones are hard because it's hard to capture.
Z equals Z, so then I just, yeah, because then all the others are just 0.
Yeah, it doesn't make sense. That might be
At least get as far as possible so I can ask some chat questions.
Yeah, it's just a solid that we have the vertices.
0, 1. Yeah. 0, 1. This whole science was
I did. I haven't done the book homework, but I did the.
So what I kept trying to do is I kept trying to do all the integrals and see whether like map out other regions. That was shown like multiple choice when you were only supposed to look at like, okay, it doesn't make sense because it has to be like t squared or ring squared. Maybe something.
The only major that I understand
Is it t?
This is the you remember
Oh, no. I already actually have my seal of literacy in another language. I'm proud of that. I have a seal of
That would just be a
I am technically so it's not bad. If you got any
That's what I wish I had that on Klingon. Because I went on just later to see how people were solving different vertices than I did. It's the same version of the book. It's figuring it out.
Well, there's an international version of the book which has every 5th problem is different,
Oh,
which is really annoying.
yeah. That is.
It's a cheaper book, so people get it. There's something I'm thinking. I'm oversimplifying with the
I mean, we know Z. Well, I mean, with the vertices they gave us, right? Z is always equal 1. Those are vertices. Except for 0, 0, 0. Oh. Oh. We have 0, 0, 0.
Yeah, 0, 0, 0, just like here.
So that's like 0, but then it's like this square thing up top, or square-ish, and then that's your
Possibly.
maybe. Right.
No, it doesn't make sense.
Let's see where. 0, 0, 0, 1, 0, 1, 0, 1, 1, and 0, 0, 1.
Alright, Jeff, come on. 0, 0, 0.
Yeah.
What's the other?
1, 0, 1.
1, 0, 1.
0, 1, 1.
So it's going to be like right there. And then 1 again?
The second one? Or what? Which
I'm
one?
sorry, yeah. 0, 0, 0. 1, 0, 1.
0, 1, 1.
0, 1, 1.
And
0, 1, 1.
And then lastly, just 0, 0, 1. So it's
Oh,
just,
yeah.
So it would be
0,
just,
0, 1. So
we have 3 planes here.
So that's what it looks like. So that is z equals 1. That is z equals 1. So now your whole problem becomes looking at what this looks like. All right, let me see. In the xy plane.
Yeah.
Okay. So that's the kind of problem. I
XY plane
was
would
expecting this to be a different, more like that other example, but now they've made this into a, you've got to do your region of inputs correctly.
Yeah. Well, we'd have to raise our XY plane up by 1.
Well, I mean, you can just,
Because I mean, if we just
Yeah.
did that would just be a point.
but you can just think about the projection of this onto your xy plane and graph these lines. You've got to figure out what
traces.
those line equations would be.
You can think about the traces, and then the line equations, like the x line, the y line, and the.
Yeah. So, let's see. So yeah, you just take all the points and you just make the z part of the point 0.
Yeah.
Yeah.
And then how
And then figure out the equation of the lines that connect those points in the xy plane. And then your let's see. I should have labeled these things. So that was 1, 0, 1. So if I push it down, it'll just be 1, 0.
Yeah.
That was 0, 0, 1, so that's right there, that's 0, 0. And that was 0, 1, 1, so it'll be 0, 1. So if I just push this down there, it looks like this.
So
now, that's, okay.
So that would be one side of the plane.
That is funny. So that was, I didn't even stop to think about the points. They all have z equal 1.
Yeah.
So the definition has to be z equals 1, but, you proved it by going through that process.
That would be